Each cell in the body needs energy to perform the functions essential for the cell's own survival, such as active transport and cellular repair, and to carry out its specialized contributions toward maintaining homeostasis, such as gland secretion or muscle contraction. All energy used by cells is ultimately provided by food intake. According to the first law of thermodynamics, energy can be neither created nor destroyed. Therefore, energy is subject to the same kind of input-output balance as are the chemical components of the body, such as water and salt. The energy is ingested food constitutes energy input to the body. Chemical energy locked in the bonds that hold the atoms together in nutrients molecules is released when these molecules are broken down in the body. Cells capture a portion of this nutrients energy in the high energy phosphate bonds of ATP. Energy harvested from biochemical processing of ingested nutrients is either used immediately to perform biological work or stored in the body for later use as needed during periods when food is not being digested and absorbed. Energy output or expenditure by the body falls into two categories: external work and internal work. External work is the energy expended when skeletal muscles are contracted to move external objects or to move the body in relation to the environment. Internal work constitutes all other forms of biological energy expenditure that don't accomplish mechanical work outside the body. Internal work encompasses two types of energy-dependent activities. First, skeletal muscle activity used for purposes other than external work, such as the contractions associated with postural maintenance and shivering. And second, all the energy expecting activities that must go on all time just to sustain life. The latter include the work of pumping blood and breathing, the energy required for active transport of critical materials across plasma membranes, and the energy used during synthetic reactions essential for maintenance, repair, and growth of the cellular structures. In short, the metabolic cost of living. Not all energy in nutrient molecules can be harnessed to perform biological work. Energy cannot be created or destroyed, but it can be converted from one form to another. The energy in nutrient molecules not used to energize work is transformed into thermal energy or heat. During biochemical processing, only about 15% of energy in nutrients molecules is transferred to ATP. The other 50% of nutrient energy is immediately lost as heat. During ATP expenditure by the cells, another 25% of energy derived from ingested blood becomes heat. Because the body is not a heat engine, it cannot convert heat into work. Therefore, not more than 25% of nutrient energy is available for work, either external or internal. The remaining 75% is lost as heat during the sequential transfer of energy from nutrient molecules to ATP to cellular systems. Furthermore, of the energy actually captured, for use by the body. Almost all expended energy eventually becomes heat. To exemplify, energy expended by the head to pump blood is gradually changed into heat by friction as blood flows through the vessels. Likewise, energy used in synthesizing structural protein eventually appears as heat when that protein is degraded during the normal course of turnover of bodily constituents. Even in performing external work, skeletal muscles convert chemical energy into mechanical energy inefficiently. As much as 75% of the expended energy is lost as heat. Thus, all energy liberated from ingested food that is not directly used for moving external objects or stored in fat, adipose tissue, deposits, eventually becomes body heat. This heat is not entirely wasted energy, however, because much of it is used to maintain body temperature. The rate at which energy is expended by the body during both internal and external work is known as metabolic rate. Because most of the body's energy expenditure eventually appears as heat, the metabolic rate is normally expressed in terms of the rate of heat production in kilocalories per hour. The basic unit of heat energy is the calorie, which is the amount of the heat required to raise the temperature of 1 gram of water by 1 degree per Celsius. This unit is too small to be convenient when discussing the human body because of the magnitude of heat involved. So the kilocalorie or calorie, which is equivalent to 1000 calories, is used. When nutritionists speak of calories, is quantifying the energy content of various foods. They are actually referred to kilocalories or calories. 4 kilocalories of heat energy are released when 1 gram of glucose is oxidized or burned, whether the oxidation takes place inside or outside the body. The metabolic rate and consequently the amount of heat produced vary depending on a variety of factors such as exercise, anxiety, shivering, and food intake. Increased skeletal muscle activity is a factor that can increase metabolic rate to the greatest extent. Even slight increases in muscle tone notably elevate the metabolic rate, and various levels of physical activity markedly alter energy expenditure and heat production. For this reason, a person's metabolic rate is determined under standardized basal conditions established to control as many as possible of the variables that can alter metabolic rate. In this way, the metabolic activity necessary to maintain the basic body functions at rest can be determined. The so-called basal metabolic rate, BMR, is reflections of the body's idealized speed, or the minimal working rate of internal energy expenditure. The BMR is measured under the following specified conditions. First, the person should be at physical rest, having refrained from exercise for at least 30 minutes to eliminate any contribution of muscular exertion to heat production. Second, the person should be on mental rest to minimize skeletal muscle tone. People tense up when they are nervous, and to prevent a rise in epinephrine, a hormone secreted in response to stress that increases metabolic rate. Third, the measurement should be performed at a comfortable room temperature so the person doesn't shiver. Shivering can markedly increase TAN production. Fourth, the subject should not have eaten any food within 20 hours before the basal metabolic rate determination to avoid diet-induced thermogenesis or the obligatory increase in metabolic rate that occurs as a consequence of food intake. This short-lived, less than 20 hours rise in the metabolic rate is the result not of digestive activities, but of the increased metabolic activity associated with processing and storage of ingested nutrients, especially by the major biochemical factory, the liver. The rate of heat production in basal metabolic rate determination can be measured directly or indirectly. With direct calorimetry, the person sits in insulated chamber with water circulating through the walls. The difference in the temperature of the water entering and leaving the chamber reflects the amount of heat liberated by the person and picked up by the water as it passes through the chamber. Even though this method provides direct measurement of heat production, it's not practical because calorimetry chamber is costly and takes up a lot of space. Therefore, more practical method of indirectly determining the rate of heat production was developed for widespread use. With indirect calorimetry, only the person's oxygen uptake per unit of time is measured, which is a simple task using minimal equipment. Recall that food plus oxygen means carboxygen plus water plus energy must transform into heat. Accordingly, direct relationship exists between the volume of oxygen used and the quantity of heat produced. This relationship also depends on the type of food being oxidized. Also, carbohydrates, proteins, and fats requires a different amount of oxygen for their oxidation and yield different amount of kilocalories when oxidized. An average estimate can be made of the quantity of heat produced per liter of oxygen consumed on typical mixed American diet. This approximate value, known as the energy equivalent of oxygen, is 4.8 kilocalories of energy liberated per liter of oxygen consumed. Using this method, the metabolic rate of a person consuming 15 liters per hour of oxygen can be estimated as follows. In this way, a simple measurement of oxygen consumption can be used to reasonably approximate heat production in determining metabolic rate. Once the rate of heat production is determined under the prescribed basal conditions, it must be compared with normal values for people of the same sex, age, height, and weight, because these factors all affect the basal rate of energy expenditure. For example, A large man actually has a higher rate of heat production than a smaller man, but expressed in terms of total surface area, the output of kilocalories per hour per square meter of surface area is normally about the same. Thyroid hormone is the primary but not sole determinant of the rate of the basal metabolism. As thyroid hormone increases, the basal metabolic rate increases correspondingly. Epinephrine also increases the basal metabolic rate. Surprisingly, the basal metabolic rate is not the body's lowest metabolic rate. The rate of energy expenditure during sleep is 10% to 15% lower than the basal metabolic rate, presumably because of the more complete muscle relaxation that occurs during the paradoxical stage of sleep. Energy input must equal energy output to maintain neutral energy balance. Because energy cannot be created or destroyed, energy input must equal energy output as follows. There are three possible states of energy balance. Neutral energy balance. If the amount of energy in food intake exactly equals the amount of energy expended by the muscles in performing external work plus the basal internal energy expenditure that eventually appears as body heat, then energy input and output are exactly in balance and body weight remains constant. Positive energy balance. If the amount of energy in food intake is greater than the amount of energy expended by means of external work and internal functioning, the extra energy taken in but not used and stored in the body primarily as adipose tissue, so body weight increases. Negative energy balance. Conversely, if the energy derived from food intake is less than the body's immediate energy requirements, the body must use stored energy to supply energy needs, and body weight decreases accordingly. For a person to maintain a constant body weight, energy acquired through food intake must equal energy expenditure by the body. Because the average adult maintains a fairly constant weight over a long period of time, this implies that precise homeostatic mechanism exists to maintain a long-term balance between energy intake and energy expenditure. Theoretically, total body energy content could be maintained at a constant level by regulating the magnitude of food intake, physical activity or internal work, and heat production. Control of food intake to match change in metabolic expenditures is the major means of maintaining a neutral energy balance. The level of physical activity is principally under voluntary control, and mechanisms that alter the degree of internal work and heat producing are aimed primarily at regulating body temperature rather than total energy balance. However, after several weeks of eating less or more than desired, small counteracting changes in metabolic may occur. For example, a compensatory increase in the body's efficiency of energy used in response to underfeeding partially explains why some diets become stuck and plateau after having lost the first 10 or so pounds of weight fairly easily. Similarly, compensatory reductions in the efficiency of energy use in response to overfeeding accounts in part for the difficulty experienced by very thin people who are deliberately trying to gain weight. Despite these models, compensatory change in metabolism, regulation of food intake is the most important factor in the long-term maintenance of energy balance and body weight. Food intake is controlled primarily by the hypothalamus. Even though food intake is adjusted to balance change in energy expenditures over a period of time, there are no calorie receptor per se to monitor energy input, energy output, or total body energy content. Instead, various blood-borne chemical factors that signal the body's nutritional state, such as how much fat is stored or the feeding status, are important in regulating food intake. Control of food intake doesn't depend on changes in a single signal, but is determined by the integration of many inputs that provide information about the body's energy status. Multiple molecular signals together ensure that feeding behavior is synchronized with the body's immediate and long-term energy needs. Some information is used for short-term regulation of food intake, helping to control meal size and frequency. Even so, over a 24-hour period, the energy in ingested food rarely matched energy expenditure for the day. The correlation between total caloric intake and the total energy output is excellent. However, over long periods of time, as a result, the total energy content of the body and consequently body weight remains relatively constant on a long-term basis. Thus, energy homeostasis, that is energy balance, is carefully regulated. Control of energy balance and food intake is primarily a function of the hypothalamus. The arcuate nucleus of the hypothalamus plays a central role in both the long-term control of energy balance and body weight and the short-term control of food intake on meal-to-meal basis. The arcuate nucleus is an arc-shaped collection of neurons located adjacent to the floor of the third ventricle. Multiple, highly integrated, redundant pathways crisscross into and out of the arcuate nucleus, indicative of the complex systems involved in the feeding and satiety. Feeding of appetite signals give rise to the sensation of hunger, driving us to eat. By contrast, satiety is the feelings of being full. Satiety signals tell us when we have had enough and suppress the desire to eat. The arcuate nucleus has two subsets of neurons that functions in an opposite manner. One subset releases neuropeptide Y and the other releases melanocortins, a precursor molecule that can be cleaved in different ways to produce several different hormone products. Neuropeptide Y, NPY, one of the most potent appetite stimulators ever found, leads to increased food intake. thus promoting weight gain. Melanocortins, a group of hormones traditionally known to be important in varying the skin color for the purpose of camouflage in some species, have been shown to exert an unexpected role in energy homeostasis in humans. Melanocortins, most notably alpha melanocyte stimulating hormones, alpha MSH, from the hypothalamus, suppress appetite, thus leading to reduced food intake and weight loss. Melanocortins don't play a role in determining inherent skin coloration in humans, but alpha MSH produced in the skin in response to ultraviolet light from the sun act locally on melanin, pigment producing cell to cause tannin. Melanocortin's major importance in our species. However, in their role, the hypothalamic alpha MSH is toning down appetite. But NP1 and melanocortins are not the final effectors in appetite control. These aqueous nucleus chemical messengers in turn influence the release of neuropeptides in other parts of the brain that exert more direct control over food intake. Scientists are currently trying to unravel the other factors that act upstream and downstream from NPY and melanocortins to regulate appetite. Based on current evidence, the following regulatory inputs to the arcuate nucleus and beyond are important in the long-term maintenance of energy balance and the short-term control of food intake at meals. Long-term maintenance of energy balance, leptin and insulin. Scientists' notion of fat cells, adipocytes, in adipose tissue as merely storage space for triglyceride fat underwent a dramatic change late in the last century with the discovery of their active role in energy homeostasis. Adipocytes secrete several hormones, collectively termed adipokines, that play important role in energy balance and metabolism. Thus, adipose tissue is now considered an endocrine gland. Some adipokines are released only from stored fat. Leptin, for example, plays an important role in energy balance. Some, like inflammatory-related tumor necrosis factor and interleukin 6, are released from adipose tissue and immune cells and contribute to chronic low-grade inflammation in excessive fat stores. Some, like visfatin, are released only from visceral fat, the deep bed fat that surrounds the abdominal organs. Visceral fat is more likely to be chronically inflamed and is associated with increased heart disease, in contrast to the more superficial and less harmful subcutaneous fat that is deposits under the skin. Some, like adiponectin, are good adipokines. Adiponectin increases sensitivity to insulin, decreases body weight, and exerts anti-inflammatory actions. Unfortunately, obesity suppresses adiponectin secretion. By contrast, some like resistin are bad adipokines. Resistin, which is released primarily in obesity, leads to insulin resistance. One of the most important adipokines is leptin, a hormone essential for normal body weight regulation. The amount of leptin in the blood is an excellent indicator of the total amount of triglyceride fat stored in adipose tissue. The larger the fat stores, the more leptin released into the blood. This blood-borne signal, discovered in the mid-1990s, was the first molecular satiety signal identified. This finding was the breakthrough that touched off the flurry of the research responsible for greatly expanding our knowledge in recent years of the complex interplay of chemical signals that regulate food intake and body size. The arcuate nucleus is the major site for leptin actions. Acting in negative feedback fashion increased leptin from burgeoning fat stores serves as trimmed down signal. Leptin suppressed appetite, thus decreased food consumption and promoting weight loss. By inhibiting hypothalamic output of appetite stimulating NPY and stimulating output of appetite suppressing melanocortins. Conversely, decrease in fat stores and the resulting decline in leptin secretion bring about increase in appetite, leading to weight gain. The leptin signal is generally considered the dominant factor responsible for the long-term matching of food intake to energy expenditure so that total body energy content remain balanced and body weight remain constant. Interestingly, leptin has recently been shown to also be important in reproduction. It's one of the triggers for the onset of the puberty signaling that the female has enough long-term energy stores to sustain a pregnancy. Another blood-borne signal besides leptin that plays an important role in long-term control of body weight is insulin. Insulin, a hormone secreted by the pancreas in response to a rise in the concentration of glucose and other nutrients in the blood following a meal, stimulates cellular uptake, use the storage of the nutrients. Thus, the increase in insulin secretion that accompanies nutrients abundance use the storage appropriately, inhibits the NPY secreting cells of the arcuate nucleus, thus suppressing further food intake. In addition to the importance of leptin, insulin, and perhaps other so-called adiposity signals in the long-term control of body weight, other factors play a role in controlling the timing and size of meals. Several blood-borne messengers from the digestive tract and pancreas are important in regulating how often and how much we eat in a given day. Two peptides important in the short-term control of food intake have recently been identified: ghrelin and peptide YY, which significantly hunger and fullness respectively. Both are secreted by the digestive tract. Ghrelin is so-called hunger hormone, is a potent appetite stimulator produced by the stomach and regulated by the feeding status. Secretion of this mealtime stimulator peaks before meals and makes people feel like eating. This falls once food is eaten. Ghrelin stimulates appetite by activating the hypothalamic NPI secretion neurons. PYY336 is a counterpart of ghrelin. The secretion of PYY, which is produced by the small and large intestines, is at its lowest level before a meal but rises during meals and signals satiety. This peptide acts by inhibiting the appetite-stimulating NPY-secreting neurons in the arcuate nucleus. By thwarting appetite, PYY336 is believed to be an important mealtime terminator. The following other factors are also involved in signaling where the body is on the hunger satiety scale. Humans are usually in environment cooler than their bodies, but they constantly generate heat internally, which helps maintain body temperature. Heat production ultimately depends on the oxidation of metabolic fuel derived from food. Changes in body temperature in either direction alter cell activity. An increase in temperature speed up cellular chemical reactions, whereas a fall in temperature slows down these reactions. Because cell function is sensitive to fluctuations in internal temperature, humans homeostatically maintain body temperature at a level optimal for cellular metabolism to proceed in a stable fashion. Overheating is more serious than cooling. Over moderate elevations of body temperature begin to cause nerve malfunction and irreversibly protein denaturation. Most people suffer convulsions when the internal body temperature reached about 41 degrees per Celsius. 43.3 degrees per Celsius in is considered the upper limit compatible with life. By contrast, most of the body's tissues can transiently withstand substantial cooling. This characteristics is useful during cardiac surgery when the heart must be stopped. The patient's body temperature is deliberately lowered. The cooler tissues need less nourishment than they do at a normal body temperature because of their reduced metabolic activity. However, prolonged fall in body temperature slows metabolism to fatal level. Normal body temperature, taken orally by mouth, has traditionally been considered 37 degrees per Celsius. However, a recent study indicates that normal body temperature varies among individuals and varies throughout the day, ranging from 35.4 degrees per Celsius in the morning to 37.7 degrees per Celsius in the evening, with overall average 36.7. Furthermore, there is no one body temperature because the temperature varies from organ to organ. From a thermoregulatory viewpoint, the body may conveniently be viewed as central core surrounded by outer shell. The temperature within the inner core, which consists of the abdominal and thoracic organs, the central nervous system, and the skeletal muscles, generally remains fairly constant. This internal core temperature is subject to precise regulation to maintain its homeostatic constancy. The core tissues functions best relatively constant temperature of around 37.8 degrees per Celsius. The skin as subcutaneous fat constitute the outer shell. In contrast to the constant high temperature in the core, the temperature within the shell is generally cooler and may vary substantially. For example, skin temperature may fluctuate between 20 and 40 degrees per Celsius without damage. In fact, as you will see, the temperature of the skin is deliberately varied as a control measure to help maintain the core's thermal constancy. Even though the core temperature is held relatively constant, Several factors cause it to vary slightly. First, most people's core temperature normally varies about 1 degree per Celsius during the day, with the lowest level early in the morning before rising 6 to 7 a.m. and the highest point in the late afternoon 5 to 7 p.m. This variation is a result of innate biological rhythm or biological clock. Second, women also experience a monthly rhythm in core temperature in connection with their menstrual cycle. The core temperature average 0.5 degree per Celsius higher duration the last half of the cycle from the time of ovulation to menstruation. While sustained elevation in temperature during this period was once thought to be caused by the increased secretion of progesterone, one of the ovarian hormones, but this is no longer believed to be the case. The actual cause is still undetermined. Third, the core temperature increases during exercise because of the tremendous increase in heat production by the contracting muscles. During hard exercise, the core temperature may increase to as much as 40 degrees per Celsius. In a resting person, this temperature would be considered a fever, but it's normal during strenuous exercise. Older is colder. The elderly naturally have lower temperatures, with midday average of 36.4 Celsius degree. Because the temperature regulating mechanisms are not 100% effective, the core temperature may vary slightly with exposure to extremes of temperature. For example, the core temperature may fall several degrees in cold weather or rise a degree or so in hot weather. Thus, the core temperature can vary at the extremes between about 36.4 degrees per Celsius and 40 degrees per Celsius, but usually deviates less than a few degrees. This relative constancy is made possible by multiple thermoregulatory mechanisms coordinated by the hypothalamus. The core temperature is a reflection of the body's total heat content. Heat input to the body must balance heat output to maintain a constant total heat content and thus a stable core temperature. Heat input occurs by way of the heat gained from the external environment and internal heat production, the latter being the most important source of heat for the body. Recall that most of the body's energy expenditure ultimately appears as heat. This heat is important in maintaining core temperature. In fact, usually more heat is generated than required to maintain normal body temperature, so the excess heat must be eliminated. Heat output occurs by way of heat loss from exposed body surface to the external environment. Balance between heat input and output is frequently disturbed by changes in internal heat production for purposes unrelated to regulation of body temperature, most notably by exercise, which markedly increases heat production, and changes in the external environmental temperature that influence the degree of heat gain or heat loss that occurs between the body and its surroundings. Compensatory adjustments must take place in heat loss and heat gain mechanism to maintain body temperature within narrow limits despite change in metabolic heat production and changes in environmental temperature. If the core temperature starts to fall, heat production is increased and heat loss is minimized so that normal temperature can be restored. Conversely, if the temperature starts to rise above normal, it can be corrected by increasing heat loss while simultaneously reducing heat production. All heat loss or heat gain between the body and external environment must take place between the body surface and its surroundings. The same physical laws of nature that govern heat transfer between inanimate objects also control the transfer of heat between the body surface and environment. The temperature of an object is a measure of the concentration of heat within the object. Accordingly, heat always moves down its concentration gradient, that is, down the thermal gradient from a warmer to a cooler region. The body uses four mechanisms of heat transfer: radiation, conduction, convection, and evaporation. Radiation is the emission of heat energy from the surface of a warm body in the form of the electromagnetic waves or heat waves, which travel through the space. When radiant energy strikes an object and is absorbed, the energy of the wave motion is transformed into heat within the object. The human body both emits source of heat loss and absorb source of heat gain, radiant energy. Whether the body loses or gains heat by radiation depends on the difference in temperature between the skin surface and the surfaces of other objects in the body's environment. Because net transfer of heat by radiation is always from warmer objects to cooler ones, the body gains heat by radiation from objects warmer than skin surface, such as sun, radiator, or burning lungs. By contrast, the body loses heat by radiation to objects in its environment whose surface are cooler than the surface of the skin, such as building walls, furniture, or trees. On average, humans lose close to half of their heat energy through radiation. Conduction is the transfer of heat between objects of different temperature that are direct contact with each other, with heat moving down its thermal gradient from the warmer to the cooler object by being transferred from molecule to molecule. All molecules are constantly in vibratory motion, with warmer molecules moving faster than cooler ones. When molecules of different heat content touch each other, the faster moving warmer molecule agitates the cooler molecules into more rapid motion, thereby warming up the cooler molecule. During this process, the original warmer molecules loses some of its thermal energy as it slows down and cools off a bit. Given enough time, therefore, the temperature of the two touching objects eventually equalizes. The rate of heat transfer by conduction depends on the temperature difference between the touching objects and the thermal conductivity of substances involved. Heat can be lost or gained by conduction when the skin, is in contact with a good conductor. When you hold a snowball, for example, your hand becomes cold because heat moves by conduction from your hand to the snowball. Conversely, when you apply a heating pad to a body part, the part is warmed up as heat is transferred directly from the pot to the body. The term convection refers to the transfer of heat energy by air or water currents. As the body loses heat by conduction to the surrounding cooler air, the air is immediate contact with the skin is warmer. Because warm air is lighter than cool air, the warm air rises while cooler air moves in next to the skin to replace the vacanting warm air. The process is then repeated. These air movements, known as convection currents, help carry heat away from the body. Without convection currents, no further heat could be disappeared from the skin by conduction once the temperature of the layer of air immediately around the body equilibrated with skin temperature. The combined conduction-convection process of dissipating heat from the body is enhanced by force movement of air across the body surface, either by external air movements such as those caused by wind or a fan, or by movement of the body through the air as during bicycle riding. Because forced air movement sweeps away the air warmed by conduction and replaces with cooler air more rapidly, a greater total amount of heat can be carried away from the body over a given time period. During evaporation from the skin surface, the heat required to transform water from a liquid to a gaseous state is absorbed from the skin, thereby cooling the body. Evaporative heat loss makes you feel cooler when your bathing suit is wet than when it is dry. Evaporating heat loss occurs continually from the linings of the respiratory airways and from the surface of the skin. Heat is continuously lost in expired air as a result of the air gaining water vapor during its passage through the respiratory system. Similarly, because the skin is not completely waterproof, water molecules constantly diffuse through the skin and evaporate. This ongoing evaporation from the skin is completely unrelated to the sweat glands. This passive evaporative heat loss are not subject to physiologic control and go on even in very cold weather, when the problem is one of conserving body heat. Sweating is an active evaporative heat loss process under sympathetic nervous control. The rate of evaporative heat loss can be deliberately adjusted by varying the extent of sweating, which is an important homeostatic mechanism to eliminate excess heat as needed. In fact, when the environmental temperature exceeds the skin temperature, sweating is the only avenue for heat loss because the body is gaining heat by radiation and conduction under these circumstances. At normal temperature, an average of 100 milliliters of sweat is produced per day. This value increases to 1.5 liters during hot weather and climbs to 4 liters during heavy exercise. Sweat is a dilute salt solution actively extruded to the surface of the skin by eccrine sweat glands, dispersed all over the body. This clear, salty sweat is the kind important in cooling the body. Apocrine sweat glands, which are located primarily in the armpits and genital area, produce a thick, milky sweat that is rich in organic constituents like proteins and lipids. Body odor is generated when the bacteria in the vicinity break down these organic compounds. There is no physiological importance of the apocrine sweat glands. There are remnants of sexual scent glands found in other species. Eccrine sweat must be evaporated from the skin for heat loss to occur. If sweat merely drips from the surface of the skin or is wiped away, no heat loss is accomplished. The most important factor determining the extent of evaporation of sweat is the relative humidity of the surrounding air. When the relative humidity is high, the air is already almost fully saturated with the water, so it has limited ability to take up additional moisture for the skin. Thus, little evaporative heat loss can occur on hot, humid days. The sweat glands continue to secrete, but the sweat simply remains on the skin or drips off instead of evaporation and producing a cooling effect. As a measure of the discomfort associated with combined heat and high humidity, meteorologists have devised the temperature humidity index or heat index. The hypothalamus is the body thermostat. The home thermostat keeps track of the temperature in a room and triggers a heating mechanism or a cooling mechanism as necessary to maintain room temperature at the indicated setting. Similarly, the hypothalamus at the body's thermoregulatory integration center receives afferent information about the temperature in various regions of the body and initiate extremely complex coordinated adjustment in heat gain and heat loss mechanism as necessary to correct any deviations in core temperature from normal. The hypothalamus is far more sensitive than your home thermostat. It can respond to a change in blood temperature as small as 0.01 degree per Celsius. To appropriately adjust the delicate balance between the heat loss mechanisms and the opposite heat producing and heat conserving mechanism, the hypothalamus must be apprised continuously of both the core and the skin temperature by specialized temperature sensitive receptors called thermoreceptors. The core temperature is monitored by central thermoreceptors, which are located in the hypothalamus itself, as well as in the abdominal organs and elsewhere. Peripheral thermoreceptors monitor skin temperature throughout the body. Two centers for temperature regulation are in the hypothalamus. The posterior region, activated by cold, triggers reflexes that mediate heat production and heat conservation. The anterior region, activated by warmth, initiate reflexes that mediate heat loss.